All right. This is Thermodynamics for Marine Engineering. And today we'll be discussing the first law of thermodynamics. So before that, let's have a sort of a review about the closed and open systems. For a closed system, we have a fixed mass. Heat and work may cross the boundary, as we have discussed previously. And in this example, we are considering the crankcase of the engine. So oil, um, so the mass of oil is constant or it's fixed, and the heat energy may cross the boundary. So the boundary is the crankcase. Okay, so this is the boundary. And next is the open system. And for the open system, mass is not fixed, but rather we control the volume or and the same thing that heat and work may cross the boundary together with mass. Okay, so mass can also cross the boundary. So one example is a steam boiler wherein uh, water goes in and out in liquid and vapor form. Okay, so we have the conservation laws, and in the conservation of mass, we have the continuity equation, and it is expressed this way. Uh, Now let me go back with this one. So I just want to explain this one further. Okay, so let's consider that you have this area. Okay, so you have an area and a certain fluid at a certain velocity. Okay, so take note of the symbol velocity. Okay, so this one. Okay, so take note of the symbol for velocity. Okay, so velocity it's like this. Okay, so there is movement. Okay, so velocity. So consider that a certain fluid is passing through this area. Okay, so it creates, so as it passes through, so just imagine that this is just a circle. Okay, so just a circle. Now, depending on the velocity, depending on the velocity, you, if if it moves farther, okay, so it moves farther in such a way that we create another surface, okay, and then another okay, sorry, another surface, okay, so another surface, and then another surface, in such a way that you now have a certain height or length, and with that you now have volume. And in this case, it is volume flow rate. And volume flow rate is simply area, okay, so area and then velocity of your fluid. And earlier, we have this equation wherein the mass flow rate is density and then uh, area and velocity. So let's check that they are the same. Okay, so they are the same. Why? Because density is simply mass per unit volume. In this case, it's mass rate and volume flow rate, then area multiplied by velocity. So as you can see, mass is cancelled. So we are left again. We go back to this equation. And going back with this equation, this expression can be like this. So you have mass flow rate, and then instead of density, we use specific volume. So this one becomes like this. So area multiplied by velocity and then specific volume. Okay, so specific volume. So the inverse of density. So volume per unit mass. And with that, we arrive at this continuity equation. Okay, so we have area. So this is velocity. Okay, so velocity and then specific volume. And in this continuity equation, we have area 1, velocity 1 over specific volume 1 is proportional to area 2, velocity 2, specific volume 2. So conservation of energy, we have the energy equation or Bernoulli's energy equation. And this is your the energy balance. Okay, so the general energy balance, if you remember in chapter 2 in our discussion. And for a non-flowing fluid, then the energy of the system becomes the change in internal energy, change in kinetic energy, and change in potential energy. For a flowing fluid, we now have this equation delta PV. So this is pressure volume. Okay, so pressure volume. Then same thing, delta U, delta KE, delta PE. Now take note that this expression delta PV and delta U is actually delta H, enthalpy. So enthalpy. So let's move on with the first law of thermodynamics under the closed system. And for the closed system, so Q net, so uh, Q in minus Q out, and then work net. Okay, so work out minus work in. For open system, okay, so for open system, uh, we have Q net minus work net, and then mass is factored out. Okay, so mass is factored out. So that's why the enthalpy is expressed in lowercase. So enthalpy 2 minus enthalpy 1. And then this is kinetic energy. So velocity 1, velocity 2. And then this is potential energy. So elevation 1, elevation 2. And G is constant, your gravitational constant. Now we have this term boundary work. So boundary work uh, is a kind of work expended when a force acts through a displacement. So there is displacement. So let's see over here. Let's consider uh, this piston cylinder assembly. And as the gas, through its pressure, pushes the piston, and so it creates a displacement. And with that, we create work, and we call that as boundary work. And boundary work is simply uh, this this integral. So we'll skip on calculus. So calculation of uh, boundary work. So I forgot about uh, this one. So let me show it to you. Okay, so um, in the energy balance in chapter 2. Okay, so I forgot about this. So it's so we have Q in, Q out, and then work in, work out, energy of the mass minus in and then out. Okay, so for boundary work, let me show you the sign convention. So again, this is just a review. So this is your system. Okay, so this is your system. Okay, so you have Q in and then Q out. So positive Q in, Q out negative. Okay, so positive, negative. Work. Okay, so work in, work out. Okay, negative, positive. Okay, so when work is positive, it means to say work is done by the system. When work is negative, then work is done on the system or work or to the system. All right. I hope I am clear with this one. So don't forget this sign convention. This is very important. Q in, Q out, positive, negative in terms of work. So this is positive, then this is negative. Okay, so work in, work out. Okay. So let's move on. Calculation of boundary work. So with boundary work, um, so we now have this PV diagram, and considering from process 1 to process 2, we take a differential strip. But as I've said, uh, the analysis is about calculus, so we'll skip on that one. But this is how the formula is derived. Okay, so you have the differential V, so the strip from here. Okay, so with the sign convention, um, we have an example here that the work of your compressor is considered negative. Okay, so the work of your compressor is negative. Why? Because we are considering the system of the air. So we do work to the air, and that air is the system that we are considering as far as the compressor is concerned. So again, the work done to the air, negative. So that is negative work for your compressor. This will be discussed in details later. All right, so let's have these processes, and we have the constant volume process. Okay, so what's the other term for constant volume process? Yes, isometric. Okay, so isometric, constant volume process, isometric process. So for the isometric process or constant volume process, boundary work is zero. Okay, so boundary work is zero. Um, we have a question here. If the working fluid is an ideal gas, what will happen to the temperature of the gas during this constant volume process? So let's consider a rigid tank. Okay, so we have a rigid tank. Okay, so this is a rigid tank, and what happened here? So for a rigid tank, volume is constant. Okay, so it undergoes an isometric process. So so let's recall that this equation for ideal gas PV MR. So considering that mass is constant, then and R is also constant, of course, then this one can be expressed as like this, mr, and then PV over T. So at any given state, so from state 1 to state 2, then it may be said that pressure 1, volume 1, temperature 1 is proportional to pressure 2, volume 2, then temperature 2. At constant volume process, or again, what's the term for constant volume? Isometric. Okay, so isometric. So volume 1 equals volume 2. So this is now cancelled. So we are now left with pressure 1, temperature 1, and then pressure 2, temperature 2. So rearranging this one. So temperature 2, temperature 1 is pressure 2 over pressure 1. So we can see that temperature is directly proportional to pressure. Okay, so temperature is directly proportional to pressure, or pressure is directly proportional to temperature. They're just the same. Okay, so going back with the question, what will happen to the temperature of the gas during this constant volume process? In this case, since pressure went down from state 1 to state 2, so temperature is lower in this case. So as we have seen, as we have seen here, pressure and temperature are directly proportional to each other. So if pressure is increasing, then temperature should increase. If pressure is decreasing, then temperature should also decrease. So that answers the question over here. Next is constant pressure process. Okay, so constant pressure process. What's the other term for constant pressure process? Yes, isobaric process. Very good. Isobaric process. So for isobaric process, boundary work. Okay, so boundary work is pressure multiplied by volume 2 minus volume 1. Okay, so let's consider um, a piston cylinder assembly. Okay, so let's consider a piston cylinder assembly, and then it is spring loaded. Okay, so spring loaded. So the spring is designed in such a way that it will maintain the pressure inside the system. Okay? So if uh, heat is abstracted, okay, so if heat is abstracted, so Q out, okay, so Q out. So as to maintain pressure, the spring will push the piston down. Okay, so as to maintain the pressure. So if let's say uh, we have instead of heat coming out, okay, so instead of heat coming out, heat energy is going in. So heat energy is going in. So in that case, if heat energy is going in, so as to maintain pressure, so the piston will now move up. Okay, so the new position of the piston will be over here. Okay. And so that is to maintain the pressure in the system. So going back with that, with this relationship, okay, so wherein, uh, mass is constant. So for an ideal gas, okay, so at constant pressure, okay, so at constant pressure process or isobaric, so pressure 1 equals pressure 2. So this one is already cancelled. So we are now left with volume 1, temperature 1, and then volume 2, temperature 2. So rearranging again, we now have temperature 2, temperature 1, and then volume 2, volume 1. So temperature is directly proportional to volume in an isobaric process. Okay, so for isobaric process. So as illustrated here, to maintain uh, pressure, so constant pressure process, so there is an increase in volume when heat energy is going in. So of course, temperature will also increase. When energy is rejected, temperature will decrease, and so volume will also decrease. So that is for isobaric process. Okay? Isobaric process. Um, we now have a question here that for this, considering this diagram, okay, considering this diagram, what is the boundary work? Is it positive or negative? In this case, since volume 1 is greater than volume 2, so from state 1 to state 2, okay, so this is volume, so pressure, and then volume. So volume 2 is less than volume 1, then boundary work is negative. It means to say work is done on the system. Negative. Is it equal to mr delta T? Yes, it is equal to mr delta T. So let's consider again the ideal equation, ideal gas law. Okay, so MRT. Okay, so MRT, constant pressure. Okay, so if this is pressure 1 and then volume 1, MR and then temperature 1 for 2. Okay, so for 2, state 2, pressure 2, volume 2, MRT 2. Now, boundary work is, okay, so boundary work, what is boundary work? So boundary work is P and then volume 2 minus volume 1. So this is the process is isobaric, so constant volume process. So pressure 1 is equivalent to pressure 2. In this case, so this will be, so so it will be like this. So pressure 2, volume 2, and then pressure 1, volume 1. Okay, so P, so in this case P, so as I've said, pressure 1 is equivalent to pressure 2. And this one becomes M R T sub 2 minus M R T sub 1. Finally, this becomes MR delta T. Okay, MR delta T. So boundary work is also equivalent to mr T sub 2 minus T sub 1. They're the same. They're the same. Okay? So that answers the question. So is it equal to mr delta T? So remember that one. It will become handy during your exam. Okay, so this time we have constant temperature process. What's the other term for constant temperature process? Yes, isothermal process. Isothermal process. So, um, boundary work this time is now expressed as MRT ln. Okay, so ln of volume 2 divided by volume 1. Uh, so other forms for boundary work under isothermal process are this. Okay, so uh, so let me show you. So let me show you this one. Okay. So again, the uh, relationship. So this time, consider a piston cylinder assembly. Okay, so let's consider a piston cylinder assembly. Okay, and so a piston cylinder assembly that is perfectly cooled. Okay, so perfectly cooled. Okay, so the system is perfectly cooled. Okay, so perfectly cooled. So if there is energy in, so if there is energy in, okay, if there is energy in, then it is perfectly cooled. Temperature will be maintained. The same thing if there is energy out or heat energy is going out, it will maintain the temperature of the system. So again, from this relationship, okay, so from this relationship, temperature 1, and then pressure 2, volume 2, temperature 2. For isothermal process, temperature is constant. So we cancel this thing out. So we are now left with pressure 1, volume 1, and then pressure 2, volume 2. Rearranging this, we have uh, pressure 1 over pressure 2, and then volume 2 over volume 1. So we can see that pressure is inversely proportional to to volume. Okay, so inversely proportional to volume. So pressure inversely proportional to volume. So if there is an increase in pressure, what will happen to the volume? It will decrease. Okay, decrease in volume. So that's the relationship. So going back to our presentation, this is the uh, diagram. It's a PV diagram for isothermal process. And boundary work is expressed as MRT ln of volume 2 over volume 1. Considering that temperature is constant, okay, so this can be temperature 1 or temperature 2 over here. Now, for this expression, ln of pressure 1 over pressure 2, okay, so volume 2 over volume 1 is equivalent to pressure 1 over pressure 2. Okay? So that is where we got this one. And then the same thing, MRT. So MRT is PV. Okay, so MRT is PV. So let me write it here. So PV MRT. So this can be pressure 1, volume 1, temperature 1. Or pressure 2, volume 2, temperature 2. So that's why we have this relationship. Pressure 1, volume 1, and then uh, ln of volume 2 over volume 1. But the ratio of this volume is equivalent to the ratio of this pressure. So again, from here. Okay, so from here, that is where we got it. So these are the forms of boundary work for isothermal process. Okay, so constant temperature process. Okay, this time we now have a polytropic process wherein it is expressed as PV to the N is constant. And N is 0 when it undergoes a constant pressure process. N is infinity for constant volume process. For isothermal process, then N is 1. For adiabatic process, so what is adiabatic again? Adiabatic process is wherein a process that no heat energy goes in and goes out. So adiabatic, okay? Perfectly insulated. Okay? So adiabatic, perfectly insulated. So K is the specific heat ratio, okay? Specific heat ratio, and that is the ratio of specific heat at constant pressure and specific heat at constant volume. So C sub P, C sub V. So we will discuss this one later. Okay. Um, with that, I would like to show you the relationships, okay, for this specific uh, ratio. Okay. So we have uh, K. So K is specific ratio, and K is C sub B over C sub B. So this is specific heat at constant pressure, specific heat at constant volume. So, and then we have R. Okay, so we have R, and that is your gas constant. Okay, gas constant. And the relationship between the specific ratio with R is this. R is the difference between the specific heat under constant pressure and the specific heat under constant volume. Another relationship. So K and then R over K minus 1. And C sub V is R over K minus 1. Speaking of specific ratio, the heat energy at constant volume process heat energy at constant volume process is M, mass multiplied by specific heat at constant volume multiplied by delta T. And the specific heat at constant pressure process, okay, so specific or the heat energy at constant pressure process, I should say, is mass, then specific heat at constant pressure multiplied by delta T. Okay, and this one is also equivalent to delta U, and this one is also equivalent to delta H. Okay, so the generic form for heat energy Q, so heat energy Q is MC delta T. Okay, so MC delta T. So now it depends if it is an constant pressure process or constant volume process. Okay, so let's continue. Uh, the boundary work. Okay, so the boundary work for a polytropic process. Okay, so for polytropic process is this equation. Okay, so boundary work is delta PV. Okay, so pressure 2, volume 2 minus pressure 1, volume 1, all divided by 1 minus n. Or PV, ln of volume 2 over volume 1. So for a polytropic process, pressure 1, volume 1 is constant. And that is also equivalent to pressure 2, volume 2. Okay. All right. So let's have a sample problem here. So let's consider a piston cylinder device that contains nitrogen as the system. So initial pressure is 1 megapascal and given a temperature of 427 degrees C. So it undergoes an isobaric process. So again, what is isobaric? Constant pressure. Okay, so constant pressure process until its final temperature is 27 degrees C. So determine the final pressure, heat transfer, so that will be Q. Then what is the work done? So the work, is it by the system? So is the work done by the system or the work is done on the system? All right, so let's see. So we have this piston cylinder assembly or device, and nitrogen is our working fluid. From the table, okay, so from the table, nitrogen is an ideal gas. So we are given R as 0.2968 kilojoule per kilogram Kelvin. So, you can find this in your table. So I gave you the table last time. So you have your table, and you should look for nitrogen. Okay, so look for R. So where is that table? So let's see. Be over here. Gas constant. So nitrogen over here. Okay, so nitrogen 2968. Okay, so 2968. And then same thing for specific heat. at constant pressure and constant volume. Okay, okay, so constant pressure and then constant volume. Okay, so for the conservation of mass, so mass 1 is equivalent to mass 2. So the final pressure is 1 megapascal. Of course, because it undergoes an isobaric process. So pressure 1 is equivalent to pressure 2. And then heat transfer is, I gave you this one earlier, so mc delta T. But for constant pressure process, this is what we will be using. So M, so specific heat at constant pressure. However, the answer is expressed in kilojoules per kilogram. So take note that uh, Q is in lowercase. So divided by unit mass. Divided by unit mass. So we are now left with the specific heat at constant pressure, then delta T. So where did we get this one? From the table. 427 is given. 27 is also given. So again, uh, this is from the table. Then next, for the closed system, we have energy in, energy out, delta E. So we are asked to get the work done or work by the system. So we will see. Okay. So solving for this one, Q net. So that is this value, and then delta U. So I already told you earlier, delta U is this formula, for this formula, specific heat at constant volume process, delta U. So rearranging this equation, divided by unit mass, again, answer will be in kilojoules per kilogram. Um, so we have answered the value for work. Okay. So what is the work done? Question is it by the system or on the system? Is work done by the system or work done on the system? What is the sign convention for work? Work is positive when work is done by the system. Okay. So work is done by the system. Alternate solution is using the boundary work formula at constant pressure process. So pressure and then volume 2 minus volume 1. And I already explained earlier that this is also equivalent to mr delta T. Since we are expressing this as in kilojoules per kilogram, so we are now left with R delta T. So R is from the table. Then delta T is this one. So that's why we got 400. And the answer is 118.72. So slight difference. Okay, so slight difference. So this is acceptable. Okay, so R, as I've said earlier, that is your gas constant. The constant of proportionality in the ideal gas equation. So PV, okay, so in this case, it is expressed in uh, unit mass. So unit mass. So PVMRT. So specific heat C. Okay, specific heat C. So the energy required to raise the temperature of a unit mass of a substance by 1 degree. So if it is at constant volume process, then so same definition, except that we maintain the volume to be constant. The specific heat at constant volume process. The energy required to raise the temperature of a unit mass of a substance by 1 degree as the volume is maintained constant. Same thing for specific heat at constant pressure. So same definition, except that pressure is maintained to be constant. And the specific heat ratio, K. Okay, so I have already shown you this one. So the ratio is specific heat at constant pressure divided by the specific heat at constant volume process. So another term for specific heat ratio is gas index. Okay, so please take note of this one, gas index. So sometimes problem statement will go like this. Uh, you are given a gas index of uh, so whatever value, let's say 1.4. Okay? So when you see the term, these terms, gas index, then that is K. Okay? K, gas index. So that's another term for specific heat ratio. And I have shown you these relationships earlier. K is a specific heat, and then the gas constant. All right. Um, let's have another sample problem. In this example, we have a certain gas given its uh, uh, gas constant as 320 joules per kilogram Kelvin and specific heat at constant volume 0.84 kilojoules per kilogram Kelvin. So we are asked to get the specific heat at constant pressure and the gas index or specific heat ratio. And for letter B, if we are given 5 kilograms of this gas and undergoing a reversible non-flow constant pressure process, okay, so constant pressure, so isobaric, from volume 1 at 1.133 cubic meter and pressure 1 at 690 kilopascal to a state where temperature 2 is 555 degrees C, find delta U or internal energy, the change in internal energy and the change in enthalpy. Okay, so uh, let's solve this one. Okay, so R. Okay, so R. Okay, so R is, so be careful with the units. So I will now express this in kilojoules per kilogram Kelvin. So that is R. Okay, so that is R. So we know that from the relationship that R, okay, so that R is the difference between the specific heat at constant pressure and constant volume. So we are looking for this term, okay, for this term. Solving for this term, we are now left with this one and then this one. Okay, so R is 0.32 plus 0.84. And that gives us an answer of 1.16 kilojoule per kilogram Kelvin. Uh, Next, we are to look for K. Okay? So K. And K is the ratio. Okay. Okay. So the ratio for the specific heat at constant pressure and constant volume. Now, I would not advise so to use this formula. Why? Because um, we will be using a derived answer. So we have a derived answer already here. So 1.16. Now the problem is, what if? Okay, so what if you made a mistake? So somewhere here you made a mistake. So you have a wrong answer for this one. In this case, if this is wrong, then if you use this value, then this will become wrong. So this equation, instead of using this equation, I will use this one, this relationship wherein K is expressed in terms of R and specific heat at constant volume. So solving for this one, I now have K minus 1, then R over this, and K now is R over V plus 1. Okay, so R, okay, so K rather, so K now is, so what is R? 0.32 divided by 0.84 plus 1, and so K is 1.38095. Okay? Now let's check. Okay, so let's check using this equation. So using this equation, so let's check it. Okay, so let's check it. Okay, so check. Okay, so let's check for that K is, for this formula, 1.16 divided by 0.84, and we get the same answer as 1.38095. Okay, so we have verified that indeed this is correct. Okay, so that is how you should um, approach this problem. Okay, so this is how you should solve this as much as possible. Again, I told you, avoid using derived answers if possible. Okay, so as long as it is possible, do not use derived answer. So instead, you use that one. So to check your answer. So in this case, I have checked that if K is correct by comparing it with my derived answer over here. So next is for we are given this uh, these values. Okay, so let me erase this one. So, or instead, I will just write it over here. I'll just erase it. Just erase it. Much better. Okay, so let me erase this. Okay, so for delta U, okay, so for delta U, this is N V then delta T, okay, delta T. Um, let's consider this uh, uh, relationship. Okay, so let's so before that, let me erase the whole thing. So let's consider this relationship. Okay, pressure 1, volume 1, temperature 1, and then pressure 2, volume 2, temperature 2. This one undergoes a constant pressure process. Okay, so constant pressure. So this is cancelled, and then we are given volume 1, but then volume 2 is not given. Temperature 1 is also given, but temperature 2 is not given. In this case, we will not be, this relationship is not useful. So what will be useful is this relationship. Uh, okay, so pressure 1, volume 1 equals nRT, temperature 1. So solving for temperature 1. Okay, so solving for temperature 1. Okay, temperature 1. Uh, okay, so pressure 1, volume 1 over nR. And temperature 1 is, this is 690. Then volume 1, 1.133. Then this is 5, so 5 kilograms. Then R is 0.32. So temperature 1 is 488.606 Kelvin. So we are now ready to use this formula instead. Uh, so mass is given. Uh, this is also given. Temperature 2 is given. And we just solve for temperature 1. So delta U, okay, so delta U is now 5, then multiplied by 0.84, and then temperature 2. So converting converting 555 into Kelvin. Okay, so converting this one into Kelvin, and that is 828. Okay, so that is 828 minus temperature 1. So 488.606. And this gives you a final answer of 14 25.45 kilojoules. So that answers the question for change in internal energy. For enthalpy, so for enthalpy, this is now easy for enthalpy. So I forgot to erase this part. Uh, Let me erase this one. Yeah, forgot to erase this. Okay, so for enthalpy, the formula is this one. Temperature 2 minus temperature 1, and delta H, so this is 5, and then this is 1.16, so this is a derived answer. And then temperature 2, 828, and then temperature 1, 488.606. And delta H is 1968.48 kilojoules. So let's check the answer. Let's look at the answer key. On the answer key, okay. So 1.16, so we got that one earlier. Then 1.381. Then so it's a slight difference. Okay, so there's a slight difference. Just a matter of rounding off. Okay, so this is 5, and then 1 for 0.45. Okay, so 0.48, so zero point 0.5. So it's a matter of rounding off. So we got the correct answer. All right. So that's the sample problem. Let's take this example. One more example. We now have steam flowing through the adiabatic turbine. So what is adiabatic? Perfectly insulated system. So perfectly insulated, adiabatic. No heat is going in and going out of the system. So we are given the inlet conditions of the steam as 6 megapascal and 400 degrees C, uh, and then velocity of 80 meters per second. Exit condition, so 40 kilopascal, 92% quality, and then 50 meters per second. We are given the mass flow rate, so 20 kilograms per second. So we are asked to determine the change in kinetic energy, and then the power output, and the turbine inlet area. All right. So, uh, so as I've said, the system is the steam that is in the adiabatic turbine. So this is your turbine. So these are the initial conditions given, and then these are the outlet conditions. So state 1 and then state 2. All right. So yes, as I've said, adiabatic, so no heat transfer is involved. Okay, so going in and going out of the system. Okay, so going in and going out of the system. Okay, so let's we will utilize these equations, continuity equation, and then of course, since a steam is going in and out, then that is an open system. Okay, so these are the equations that we will be using. All right. So Um, so we just, okay, so let me be clear with this one. So there's no change in elevation. So this is zero. We are given velocity. So we need to use this formula. So this one, so this is meters per second. Okay, be 2000. And then enthalpy. And then since we are just considering the turbine, then there is no work in. And the assumption is that this is an adiabatic turbine, so adiabatic process rather. So there is no energy going in and out. So heat energy rather. So no heat energy going in and out. So this is zero. So this is zero. So we are now left with this equation. So arranging. So we are now left with work out. So negative work out. So rearranging, we are now left with negative of this expression. Okay, so yeah, I already explained this one. This is cancelled. So this is 0, 0, 0, and then um, we are now left with negative work. So final equation will be like this. All right. Enthalpies are read and computed. So using the steam table at state one. Okay, so at state one, uh, here. So 6 megapascal and then temperature is 400 degrees C. So steam is superheated. So let's see why it is superheated. So what's this? Table A4. So table A-5. Oops. Okay. Okay. So what's the pressure again? What's the pressure? 6 megapascal. Okay, so 6 megapascal. Okay, so here it is. But then the saturation temperature at 6 megapascal, 6,000 kilopascal, is 275.59. But the given temperature is 400. And so we conclude that the steam is superheated. If it is superheated, and then we now go to the superheated table. So let's look for the entry 6 megapascal. Okay, so there we are. 6 megapascal and then temperature at 400. So from the table, we get enthalpy 1 as 3178.4 and then specific volume 1 to be this value. Okay, so specific volume and then enthalpy. So knowing those values, we now go to state 2. So since we are given uh, quality 92%, then we know that it is in the liquid vapor region. So at state 2, given 40 kilopascal, let's proceed to okay, so 40 kilopascal. So there you go, 40 kilopascal. And then from this table, we get the values of enthalpy. So for H sub F and H sub Fg. And we now compute for enthalpy 2, knowing that enthalpy at state 2 is this expression. So we have discussed this last time in chapter 3. We have discussed this one. So X is quality. So that is 0.92. This is from the table. From the table. So we now get an answer 2450.5. So what else? What else do we need? So change in kinetic energy. We can now, of course, this is readily available. Um, so again, this 2000 is, so the formula, of course, is 1/2 mv square. Okay, so just to be clear, formula is 1/2 mv square, but this is just a conversion factor. So you multiply it or you divide it by 1000. So answer is expressed in kilojoules per kilogram. So per unit mass. Okay, so per unit mass. Velocity 2 is given and then velocity 1. Okay, so negative. And then uh, next is uh, power output. Okay, so workout. So earlier we have, so that's why we solve for enthalpy. Okay? That's why we solve for enthalpy. So we have negative 20, negative 20. Flow rate is 20 uh, kilograms per second. And then this is from, these are the values that we got earlier. So enthalpy 1 and enthalpy 2. And then, of course, this is your kinetic energy uh, in kilojoules per kilogram. So kilogram is cancelled because this is 20 kilograms per second. Okay, so per second. So that will be kilojoules per second. Okay, so kilojoules per second. So final answer is 14.6 megawatts. Okay, so you try this on your calculator. Uh, During your review, try to answer this without looking at the solution. Finally, for the turbine inlet area, so we will now use the continuity equation. So this one, that mass, so mass flow rate is, okay, so area multiplied by velocity divided by specific volume. So rearranging, so we solve for area. Okay, so we solve for area. The specific volume 1, that is from the table at state 1. Okay, so then mass flow rate is given and then velocity is given. So we now get this answer. And converting it into square centimeters, then this is the final answer. Okay, so uh, I leave you with this practice problem. You do this on your own. So an adiabatic gas turbine, again, uh, be careful with the units and then take note of the terms. So in this case, again, adiabatic. So just the previous example. So no heat is going in and out of the system. Okay. So you are given pressure. So this is your inlet pressure and then outlet. Okay. So air enters the turbine. So you're given a uh, the area of the turbine, then given the velocity, and then you have area 2, so 1 square meter. So we are to determine the mass flow rate of air through the turbine in kilograms per second and the power produced by the turbine in megawatts. So we are asked to refer to table A-17 to read the enthalpies. Because the working substance is air. Okay? So be careful. So air. So air, that is your working substance. It's not water. So that's why we are to check table A-17. And the final answer is, or R. Okay, so the answers are 46.9 kilograms per second and 18.3 megawatts. Okay, so that's it for today. I uh, I hope you practice on this one, and I'll see you next time.